Now, I want to begin by telling you a short story about my mother. My mother, like many other women of her generation, never stepped a foot into a classroom. We asked why. And her father, my grandfather, refused her to go to school because she was a woman. When her time came, she had her own family. My mother transformed her world by ensuring that all her 8 kids, boys and girls, went to school. She was a great inspiration. This month of March, Women's History Month here in the United States. We pay tribute to the generations of women whose commitment to nature and the planet have proved invaluable to society. So please, I want you to help me give them a round of applause for all the contributions they make. Let's give them all a round of applause. To highlight the contribution of women to science, we invited Eugenia Kearney, a distinguished professor of meteorology at the University of Maryland, College Park, and a woman of many firsts. In 1971, for example, she was the first woman to get a doctorate degree at MIT. Big thing that time. In 1973, she was the first woman to become a professor in the same department at MIT. Of course, in 1979, she came here. She was also the first woman to become the branch head for global, for GMAO, what we call today GMAO. So without a doubt, she's going to talk about her remarkable journey and also the driving forces that shaped her career. In those few remarks, ladies and gentlemen, I'll be welcome our distinguished speaker, Eugenia Kearney.
I cannot, well, you can see that I have many friends here, and I'm so happy to see you all, and I'm grateful that, that if you are not my friend, you came anyway. I really feel like I've been incredibly lucky, and I was just luck that has helped me go in this. Wow, there's another friend coming. So I am very moved to be talking about my life, so to speak, here, because I really feel like Goddard is my second home. Yeah. I'm very grateful. So I'll go more or less quickly or not over my life. I'm quite old, as you can see. I was born in Buenos Aires, and I feel that's one of my good lucks because of what we will say. I was the 7th out of 8 children. My mother was 42 when I was born, and so I always thought I would study medicine when I was in high school, and when you finish high school, you go directly to the faculty or school that that you choose as your major. So I was going to go, and on the last day of classes of high school, a friend told me that I shouldn't study medicine. I was good in math. I should study physics, and that day I changed to physics. And so I went to the School of Sciences of the University of Buenos Aires, which was amazing, amazingly good. It was so good that I felt when I went to MIT, wow, this is easy compared to Buenos Aires. And I was studying physics and loving it, but my mother found that there was my father had died when I was 14, and we were rather poor, and my mother worked to keep my sister and I. And she saw that there was an advertisement for a competition for scholarships for meteorology from the National Weather Service in Argentina, so she just changed my major from physics to, and signed me up. I would like to mention Rolando Garcia was the dean, and he died recently in his 90s, and he was a famous meteorologist that directed FIGI, the first global GARP. GARP experiment, and Charney said that it was successful because of Rolando Garcia, but he was a teacher and the dean of the School of Sciences, and he made it so good. And I enjoyed very much, I loved, discovered that I loved science once I was there by chance and meteorology, but after I got my degree and I was a teaching assistant, there was something called the Night of the Long Batons, which are the police batons. And in Argentina, like in all of South America, it used to be that there were military dictatorships taking power all the time, or frequently, every few years. And they decided that the university was too free or something, and they attacked the university, and in particular the School of Science, the building of School of Science and others, and they just beat everybody, including the dean, and so many hundreds of the faculty and assistants resigned, and I resigned also. And that's, then Rolando Garcia talked with Charney. He was a good friend of Jules Charney, and he recommended me, and I went to MIT. But that was really, in a way, my good luck, although it was. So I did my PhD at MIT with Jules Charney, who was an incredible, amazing mentor also. But I had several cultural shocks. One was about women. I was in the School of Sciences, about 40% of the students were women. So I didn't know anything about the US, except that it was much more advanced. So I assumed that at MIT it would be 50% women. And then I found that I was the only one. And I was also surprised about the fact that the students were competitive. They wouldn't help each other. And I was used to that if we had a test, for example, and somebody didn't know an answer, and they would send me a piece of paper, and I would write it and send it back. And I thought, if that's the least that I can do. It seemed obvious. But that was not the case. And I actually, one of the students was very kind and said to me, Norm Phillips was one of the creators of numerical weather prediction and was teaching numerical weather prediction. So this student told me, we were feeling sorry for you. Not only you are a woman, the only woman, but you are Latina, because I was from Argentina. But he said, after I started answering the questions that Norm Phillips was asking in class, they stopped feeling sorry for me.
They felt sorry for the others.
So I had to do a thesis, and I was worried that I would never be able to. And then I thought maybe if I have if I become pregnant, I will have an excuse if I fail. So I got pregnant, and I remember I was so, Charney was away, and Norm was my boss, and I went to tell him that I was pregnant, and I was so scared that he would say, "What? We wasted 2 years of research assistantship." But we were walking, and he stopped, and then he thought for a couple of seconds, and then he said, "Well, now you are going to be creative in 2 different ways." Now, I thought that was so kind. And actually, I did my thesis on the atmosphere of Venus, trying to show that the hypothesis of Goody and Robinson, that the deep atmosphere of Venus was very, very hot. I forget, but it's in probably 300 K. Was because the sun during the heat, the difference between day and night, let's say, or pole winter and summer, would drive would heat and cool the clouds, and then that drive a deep circulation, and that would make the atmosphere adiabatically stratified. So I did my thesis on that, and honestly, I felt there is so little known about Venus that if I make a mistake, they won't find it. And Charney, I only saw him every 2 or 3 months, but every time he was so inspiring. He had to remember what I was doing first, but after that, he was incredibly inspiring. And I did first, I used the Boussinesq, which has basically a constant density, and drove the model from the top, and I did get a deep circulation, so that agreed with Goody and Robinson. But then I did a quasi-Boussinesq where the density changed substantially from the top to the bottom, and then there was only a tiny curve getting in, but all the others were at the top. And I said to Charney, "Well, maybe qualitatively it's still true." And then he looked at it and he said, "Maybe Goody and Robinson are wrong." And that was the most amazing thing that I learned, because I was so had blinders trying to prove what I was trying to prove, that they were right, that I just couldn't see it. And that has been the most important lesson I ever learned in science. Then, after I finished, I went back to Uruguay in 1971. And my husband, at that time, Alberto Rivas, the father of my son, got actually, when we came back to MIT, because in Uruguay, another military dictatorship took over. So we went to Uruguay, not to Argentina, because in Argentina there was a horrible, horrendous military dictatorship that disappeared 30,000 people, many of my friends also. But it didn't make sense to stay in Uruguay when democracy was also collapsing. So we came back to MIT, and my husband got accepted by the MIT Department of Linguistics and did his thesis with Noam Chomsky, which fills us all with pride, given who Noam Chomsky is, in addition to being the best linguist. But we separated, and we came back to MIT because Charney offered me a postdoc. And at that time, I started working with Milt Halem at GIS. How many of you know Milt Halem? Okay. And he was really my major mentor. He screamed at me and taught me to be strong, and I learned a lot from him. I started before, while I was at MIT, developing a fourth order model at GIST for Milt Halem. And a fourth order model is supposed to be more accurate than a second order model like they were at that time all. And then another of my good lucks, Norm Phillips went to work to NCEP to help with a numerical weather, operational weather prediction. And since I was the only one that was interested in numerical weather prediction, I replaced him teaching NWP. And then I became an assistant and then an associate professor. And I remember when Lorenz, who was the chair of the department, said that they had considered my promotion and that they had promoted me to associate professor and that I might or might not get tenure in the future, but not at that time. And I said at that time, I better go. Milt had started what is, I guess, GMAO now. So he recruited and mentored me, and he was head of the 9/11 branch, which was called at that time Global Modeling and Simulation. And I should say how he recruited me. I used to come because I was developing that model for him. And then I went crying into his office and said, Milt, Alberto and I, my husband and I are separating. He's leaving me. And he said, great. And then he said, you can come here. And I thought, what a harsh man. And then immediately after I felt so happy. So that was the best thing that he could have said to me at that time. And we had two branches, and one was climate, which was, Shukla called them, no, not branches, sub-branches. Shukla called them twigs. Yeah. So he was the head of the climate twig, and I was head of the weather twig. And I also learned an awful lot from Shukla. I learned from Shukla how to fight and stand for your rights and not get run over. Yeah. But in our branch of weather, we did mostly experiments on satellite data simulation, trying to show that satellite data was useful. And I really learned so much there. And I would like to say, coming to Goddard had another wonderful result, which was that I met Bob Cahelan on my first year on the phone. I tried to convince him to come, that I was living in a great place, which it is Greenbrier, and he's been like my brother. Yeah. So I'll say a few words about my fourth order model and the Arakawa model. The fourth order model was a very coarse resolution for current times, 4 degrees by 5 degrees. And we wanted to do lots of experiments on data assimilation. And so people were using a higher resolution. It was, the Arakawa model with that resolution was not very good as a forecast model. So people were saying, like Wayman Baker was saying, we should use the 2 degrees by 2.5, which is 10 times slower. And I developed my fourth order model, and contrary to the predictions of Arakawa and others, it worked perfectly well, and it was as accurate as the model that was 10 times slower. So it became our workhorse, and it was used for maybe 15 years at NASA. And so we did many experiments on January and February 1979, the FIGIT time, and which are equivalent to reanalysis. And the Yale means look at
President Storm, wasn't it?
Yeah.
the President Storm, yeah. But we did experiments with and without, sorry, if you don't behave.
Shut up, Joel.
So we did with experiments with and without satellite data to try to show that the satellite data was useful, and indeed it was very useful in the southern hemisphere, but in the northern hemisphere it was useful half of the times. But then I looked at other things like time averages, and I found that there were, both with and without satellite data, there were stationary, very large amplitude waves over South America. And Yale Means, who knew everything about meteorology, said there are no waves like this. So I said, wow, this is an opportunity, my good luck. And we discovered the South Atlantic Convergence Zone. So Milt was promoted to division chief in computers, and Shukla founded COLA, the Center for Ocean and Land and Atmosphere, and left. And I was promoted to replace Milt. And you can imagine that Milt has a certain style, and I couldn't imitate that. And on top of that, it was all men, the branch, not just men, aggressives, young scientists, like Joel Susskind. I mean aggressive in a nice way.
Okay, good.
Sorry. And I just couldn't. Milt had a style in which he enjoyed when, for example, Shukla and I fought or something, he kind of liked that, but I didn't. So I followed. When I was in Boston, in Cambridge, I went to a human rights organization that was organized by a Quaker woman, and the first day she said, "What we are going to use the Quaker method. Everybody can say what they want, and we work by consensus." And I thought, wow, good luck with that. But somehow it worked, and actually I decided to use that method, and it worked incredibly well. Everybody was so cooperative. David Randall and George Susskind and all those other people did not fight at all. And actually we became very, I think, more productive. And then after a few years, and Max Suarez, and yeah, all the wonderful, wonderful people that we have. So I was invited to go to NCEP to direct the Environmental Modeling Center, which at that time was called Development Division, by Bill Bonner, the director. And in my go-away party, David Randall said that we had changed from a dictatorship to the People's Republic of 9/11. And then I became the director of EMC, which was before, at that time, Development Division at NCEP, which was then National Meteorological Center, had fallen way behind ECMWF. It was embarrassing. And trying to change that was very hard, and I also used the Quaker approach, and also I don't have time to tell the second approach, but the people had models that they personally developed and nobody else touched. And for example, the global model, which was a very good spectral model, was developed by Joe Sella. And when somebody wanted to use it, he would give him the compiled version only. So the head of the branch, the global branch, who was Masao Kanamitsu, who was very, very good, he alone recoded the whole model, and that was the experimental version. And then it had to be passed to the operational, which only Joe Sella allowed people to. And I had to change that because it was impossible to make progress like that. But we changed it, and actually, in a couple of years, the skill gap between ECMWF, which was huge, became much smaller, almost close to zero. It was never, sometimes it was zero, but it didn't last, but it was much smaller. And in addition, we were the first ones to implement 3D bar, which was work by Parrish and Derber, and we were also first by a week to implement operational ensemble forecasting, which was based on an idea that postdoc Toth and myself invented and worked very well. And this allowed extending the fact that we were having ensemble forecast allowed the forecasters to, and the TV, the best TV forecasters, the most intelligent, were the first ones to do it. They extended the public forecast from 3 days to 7 days, and I'll explain why. This is a wonderful example that I put on the cover of my book because it's a historic example of the first actually it was a 6-day forecast, but the human forecasters only saw it the following day. So by then it was 5 days only. But it showed, it's a spaghetti plot, and it shows that all the ensemble members are looking like the black line, which is the verification. And so they were all predicting a blizzard in the East Coast. And this was the first time in anywhere that a 5-day forecast of a blizzard was made, because before the model would predict maybe a 4-day blizzard, but then the 3-day didn't have it. And so the fact that all these forecasts agreed was what gave the human forecasters the courage to predict. And then after that, pretty soon, the forecast became 7 days, not 3 days. And then another thing that we did was the ENCE-PENCAR reanalysis. We needed funding. It was horrible to think of the budget all the time. And so I wrote a proposal to do a reanalysis with Proding from Shukla, who had the vision that a long reanalysis would be useful. And I based it on my experience at Goddard doing reanalysis again and again with different things with January and February 79. And the fact that we had done experiments without satellite data showed me that it was possible, even though the forecasts were much less accurate, still, for example, the time averages were almost identical with or without satellite data at 500 millibars or 200 millibars. So I felt it was worth doing a reanalysis as far back as possible, which was 1948, and we did that. And I was at that time, we had a race with ECMWF, which was also doing a reanalysis, but they were kind of angry when they would tell me, Eugenia, you know that you cannot do reanalysis before the satellite data, but I knew that it would be useful anyway. And so after that, of course, they also went back to the pre-satellite data. But I was a member of another stroke of luck. I was a member of the board of directors of the AMS at that time, and the organizer explained that they were starting to think of creating a CD-ROM as an appendix. And I almost fainted because I thought, wow, we could put the data on the CD-ROM and then it will go to 13,000 people or whatever. And we did that, and we made it extremely user-friendly and used Shukla's, Kola's grads, and it was a sellout, and there was no way that the European Center could compete with that. They have what we did is popularize it, and basically it was compared to ERA 15, it had not only disadvantages but also advantages. It was much more continuous, and it did a number of things. So after I was thinking I would stay at NCEP 3 years or so, but I stayed 10 years, and then my second husband, Malisdik, kept telling, power corrupts, and it's true, power corrupts. And so I also thought, after 10 years, I'm going to become an obstacle to progress, not a help. So I asked my kind boss, Ron McPherson, and he allowed me to step down. And I think I was the only senior executive service person to ever step down. And actually, I was surprised that I didn't feel comfortable anymore, that the attitude of the people, to my surprise, changed when I went from being the boss to not being the boss. So I felt uncomfortable and actually went to Oklahoma. I was invited and learned a lot there. And then I applied to become chair of the Department of of Meteorology at Maryland, and became what they call professor and chair. I worked a lot on improving things, and we have a new curriculum that is really focused on earth sciences, and it's very, and actually the position of the department has gone up quite a lot, and it's among the top 4, so according to the last NRC revision. So that was very, very good. But I had horrible administrative problems, which was a surprise to me, because we had a horrendous secretary that just made life impossible, and I had to spend, actually, one of my colleagues said, the greatest achievement that you are going to have is to almost get to fire the secretary. But I was able to fire her. But so so I stepped down, and I became. They kindly gave me this position. I wrote my book, and I should be writing the second edition, but I'm 2 or 3 years late, and I get scolded all the time. And amazingly, this year the AMS gave me 3 awards. There was a symposium, and I became an honorary member, so I don't have to pay. And the most important thing was that I got the Joanne Simpson Mentoring Award, and with a very nice thing that says that I give a lot of my and to my younger colleagues, and I feel that that's very, very close to my heart, especially having had the honor of meeting Joanne Simpson and working with her at Goddard. Quickly over current work that we are doing, but without going in depth. I realized that I love data assimilation, and I understand it also, which is kind of difficult. And so in my book, I try to explain it very, very simply first. And people like my book, especially because it's clear. So Ensemble Command Filter became, as soon as I saw a Canadian talking about what he was thinking of doing an Ensemble Command Filter, I said, this is the way we should go, but I couldn't convince my colleagues at TENS. But we developed that at the University of Maryland. We developed with Brian Hunt, who is a genius in applied math, invented this method, and I created several extensions that make it more powerful. And a former student of Jim Carton and I invented a new hybrid, and they both have been adopted by ECMWF that don't adopt something unless it's good. And I'm interested in doing new applications of data assimilation, in particular strongly coupled ocean-atmosphere data assimilation, and something which we call a proactive quality control. And I'll say a few, I'll finish by one. So in the classic approach to data assimilation, we have an analysis cycle, and the analysis cycle has a model that makes a 6-hour forecast, which is the background or first guess, and that's combined with observations, and the analysis is the optimal combination of this, and that produces initial conditions for the model, and it goes on. But now, I think what for the future, what we have to concentrate is in these extra arrows, the data assimilation, which is the only time in which we have the observations and the model right close to each other. We have to use this data assimilation to improve the observations and improve the model. And that's what is part of what I'm doing. So the simplicity and power of Ensemble Command Filter should encourage the use of data assimilation for improvements beyond its main goal. The main goal is to combine optimally observations and model forecast. And this is basically mostly done. The advanced methods like 4D bar and Ensemble Command Filter are probably as good as it can get, plus some extensions or additions or something. But we should also use the data assimilation to improve the observations and improve the model. Also, do more truly coupled data assimilation. Example, the ocean and the atmosphere are coupled, and obviously the best data assimilation should be very clearly coupled, and that has not been done so much, although Randy Koster yesterday told me that the GMAO is working on a strongly coupled ocean atmosphere model. And I would like to hear about that if any of you is working on that. But in addition, I think there is something which really worries me, which is the sustainability of the world and the future. And the Earth system models used by IPCC have many submodels, but they don't include the human system, which totally dominates the Earth system. So, and even the integrated assessment models, they include, for example, industries or agriculture, but they don't have population. So if the model runs out of food, the population keeps increasing like the United Nations predicts. So it's impossible to have a realistic system because they are not coupled. So we should do data assimilation of the coupled Earth system, human system. And before I talk about that, I'd like to mention the standard data assimilation has a data assimilation for the atmosphere, and that atmospheric data assimilation assimilates only atmospheric observations. And the ocean assimilates only ocean observations. So the systems don't see each other observations. So what we developed is a single data assimilation system that receives the observations, the forecast of the observations from the ocean and the atmosphere, and also compares it with the observations. But the observation localization allows the ocean to look at the atmospheric observations and allows the atmosphere to look at the ocean observations. So this is completely new. And it's an idea of Miyoshi and Penny. And I will just show from my student, Travis Luca. He's doing experiments with the SPEEDY model, which is a simple global GCM, and the NEMO, which is a widely used ocean model. And he will do only atmospheric observations. He has done only atmospheric observations, and we'll see the result of that. And basically, these are the errors in salinity, and the full line is the strongly coupled errors where the ocean sees the atmospheric observations, and this is in the standard way. And you can see that for every, the tropics, northern hemisphere, southern hemisphere, it's very clear, especially here, at 500 meters, when the ocean sees the atmospheric observations, the error is this. When it doesn't see it, it's like that. So it's clearly making a big difference, and same with the temperature. And for example, in the standard weak coupling, these are the errors, and in the strong coupling, these are the errors, and the difference are these, which are almost all positive. So in other words, it's an improvement. So let me skip this. So it's very important, especially for climate prediction, to have the ocean observing the atmosphere and the atmosphere observing the ocean observations, not just be parochial. So another student did what we call a proactive quality control, and I'm not going to describe how, but it's using the local ensemble transform Kalman filter and the ensemble sensitivity to forecast. Ensemble forecast sensitivity to observations. And we developed a few formulas, and we found that we could find whether each observation improves or makes the 6-hour forecast better or worse. So if it's better, and this happened to be modest winds in high latitudes. If it's better, it's blue. If it's worse, it's red. And you can see that we detect, according to our method, quite a number of observations that are making it worse. And then we drop those observations that we determine have a negative impact and make a 24-hour forecast, and the difference between the two forecasts it shows blue, which means it improved. So this is a very powerful thing, and it should, this methodology should accelerate the optimal assimilation of new instruments, because currently, if you have a new instrument, before you accept it operationally, you have to show that it improves the system, and you have to wait, do lots of 5-day forecasts to find a sliver of a positive thing. Whereas this can be done in 6 hours. And another thing is parameter estimation and estimation of bias using data assimilation. And my student Jisung Kang, a woman, half of my students are women. She invented something called variable localization, and then she did this, which was to obtain the carbon fluxes from the surface in a simulation without, these are the true carbon fluxes after in the winter and summer, or the other way around. And this is what she found using parameters, estimating the surface carbon fluxes as a parameter, not not trying to invert or do anything like that. And this is by far the best result ever obtained for this. So it just shows that one can use parameters, even evolving parameters, using the data simulation. And maybe I'll say a few words about the Earth and human system. It is completely dominated by the humans. The Earth system is completely dominated by the human system. And in order to understand their interactions, we need to couple them bidirectionally with feedbacks. And currently, IPCC models and even integrated assessment models don't include population. It is exogenously obtained from UN tables. The UN creates every year tables of how they project the population, and that's what's used in the models, and that doesn't make sense. It's exactly as if we were trying to predict El Niño, and we had a very good atmospheric model, and then we got the sea surface temperature from tables from the UN. It doesn't make sense. But that's, and part of that is that population is a taboo subject. So thanks to a grant that Bob Cahalan kindly gave us, we were able to pay a student. This is basically says that this is an IPCC model, and they are very proud because they have coupled more and more of the system. But without fully coupling, we could not predict El Niño, and we are still missing the most important component, which is the human system. And if we don't couple it, we cannot get realistic results. So we think this is a type of a fully coupled system that makes sense. But and then we developed a Moteshare from a grant that Bob Cahalan gave. Moteshare and Jorge Rivas, who is the baby that I had at MIT, but is now my collaborator, and myself wrote a paper where we represent the human and nature as sorry, as a predator and prey, human and nature like a predator and prey, where the predator is the population, prey is nature. So the population is all the time using nature, but we decided to separate the population into rich and poor, and we developed very simple equations, and the results were very striking. And if we find that if the different, this is an example with high inequality. The rich make 100 times more than the poor, and nature gets depleted. There is a huge wealth accumulated, but when the population goes over the current capacity, the wealth starts decreasing, and then there is not enough food for the poor, which start dying, and then the equivalent elites, which are, this is multiplied by 100 because of that this is their consumption. They think that they can last like 100 years longer than, or for 100 years they see that the poor are dying, but they are doing great because they have a lot of wealth accumulated. But eventually they also die. So this economic crisis provides a very obvious indication that the population has grown beyond the sustainable level for the ecological system. And also, it's very important that this happens also. It's impossible with a high inequality like this, it's impossible to not to collapse. That's what we found. So, but it's possible to, if we change the parameters, for example, if we reduce the depletion per capita to its optimal value and the inequality from 100 to 10, it is possible to reach a steady state and survive very well. So it's not a doom situation. We need policies, changes in policies to reduce the depletion per capita, reduce the inequality from 100 to 10, and also reduce birth rates. And this is my last thing. Consider the impact of adding fossil fuels. So, because in the previous here we have only regenerating nature like fisheries or forests or crops, but suppose that we add non-renewable energy. This was the result before. The system collapsed at about 500 years. So what happens when we add fossil fuels? We add the fossil fuels, and what we find is that the collapse is postponed by about 200 years, and the population is increased by a factor of 20. So, and that is eerily similar to what happened since the Industrial Revolution, because we started using the fuels that it took hundreds of millions of years for nature to accumulate, and we are using it in about 200 years, and the population can grow much more because we are basically eating fossils. And so this is kind of scary. So, summary. This is what I talked about now, and thanks.
So we have time for a few comments, questions.
What, as you integrate the human system into the Earth system, what would be the first parameter or variable you would put in your human system model? Or what?
That's discussed in more detail. Basically, we are planning to include, and we have done a model for for water. Sorry, this is a little bit old, but basically we have population, demographics, and everything. For example, the agriculture, there is agriculture gives food per capita, and then the population determines whether there is enough food to maintain the population, and if there is not enough, then it converts some extra land into agriculture, and everything has to be with feedback, two-way feedbacks, and very important. For that you need policies. It shouldn't be determined by the corporations what the policies should be, in my opinion. Yeah.
What changes when you change inequality from 100 to 10? Do people start sharing more, or where does?
Yeah, the equations are like this. The consumption, the wealth is the production, where only the production has a depletion rate per capita, and only the commoners, which are the poor, work. And then the wealth adds the production, and then it subtracts what the commoners consume and what the elites consume. And so the production is this, like here, and then the population of the commoners, the poor, this is the number of poor times the subsistence salary, so to speak. And then the elite manages but doesn't work, but they consume kappa times more.
I want to commend you for taking on this kind of work and making it actually understandable. So maybe you can't answer this briefly, but when you present this sort of thing to various audiences where you have, what kind of reactions do you get?
I remember in WCRP had in Denver, and my talk was the last one, the last day, the last session, and it was rather full, and I got many people that said that this was the best talk they had ever heard. And I should say, before our paper was published, a blogger from The Guardian wrote a very positive thing, but he put a title that included a NASA study, and that produced a big list of attacks by, I guess, NASA Watch and things like that. But what's his name? The guy that works, the astronaut, Pierre Sellers handled it very well. But so we had to say how come NASA had supported this, and it was that not that the NASA supported this, but this blog went viral, and there were 40 million hits of this blog. And our paper had been rejected, but we fought, and it was accepted. And once it was accepted, in 2 or 3 weeks, it became the most downloaded paper.
So it's going to outnumber your other one there.
Yeah.
Okay, so let's thank Eugenia one more time.
I really feel like I came home and I saw my family. Thank you very much.